Good day, students. For today, we are going to look at electric field. Specific objective. At the end of the lesson, you should be able to define electric field and the electric field intensity. Give expression for electric field intensity and state the unit. Define electric potential and state the SI unit. Then solve questions on electric field and potential. Now, electric field. Electric field is a concept used to describe how electric forces will act on a charged particle in space. For instance, if a test charge is brought within a region of space containing an electric charge such that the distance between them is r, the two charges will experience a force F given by F is equal to Q1 Q2 over 4 pi epsilon 0 r square. The region of space around Q1 within which a test charge Q2 experience a force is called the electric field. Okay, you see the pattern of the electric field shown in the two diagrams. A represents the pattern due to a point charge, a test positive charge, while B is a pattern due to two parallel plates capacitor. Now, electric field is therefore defined as a region of space in which electric charge experiences an electric force. The electric force is represented by electric lines of force. Now, electric line of force is defined as imaginary lines drawn in such a way that the direction at any point is the same as the direction of the field at that point. It is also defined as the path which an isolated small positive charge will follow if placed in the field. Now you see the pattern. So that is the line of force due to unlike charges and like charges. As we know that unlike charges attract while like charges repel. So the first lines of force represents the attractive force between two unlike charges, while the second one represents the repulsion between two like charges. Okay. Then properties of electric line of force. Number one, the line follows the path of a freely moving positive charge. Number two, it originates at the positive charge and terminates at the negative charge. Number three, the field lines cannot cross or intersect one another. Then number four, the density of the line, that is the number of line per unit area perpendicular to the line, at any point is proportional to the magnitude of the field at that point. So this particular point is telling us that the more the line, the higher the strength of the field. It's telling you that when the charges are concentrated at a given area, it means the electric field is stronger there. But when they are widely spaced, the electric field is weak there. Okay. The number 6. Okay, number 5 or 6. The lines are drawn uniformly spaced, entering or leaving an isolated point charge. The number 6. The number of lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. The number 7. The field lines are usually curved. They are only straight for a point charge in a parallel plate capacitor. We see it in the pattern shown above, where we have the lines of force being parallel to one another, showing that it is what? A uniform field from what? Two parallel plate capacitor. Okay. Now, electric field intensity. The electric field strength, also known as electric field intensity, is defined as the electrostatic force experienced by a unit positive test charge at that point. Simply, it is the force per unit positive charge at a given point in an electric field. So it is given by E is equal to F over Q. So where F is the force, Q is the charge. The unit of E is in Newton per coulomb. Then E is a vector. So therefore, electric field is a vector field. So we now say the electric field due to a point charge Q at a distance r meters away is given by E is equal to Q over 4 pi epsilon 0. Example 1. The positive test charge has a magnitude of 3.0 times 10 to the power minus 8 coulomb and experiences a force of 6.0 times 10 to the power minus 8 Newton. Question A. Find the electric field intensity that the test charge experiences. B. Predict the force that a charge of plus 12 times 10 to the power minus 8 coulomb will experience if it replaces the test charge. Now, solution. We see that electric field intensity E is equal to F over Q. So it will be equal to 6 times 10 to the power minus 8 divided by 3 times 10 to the power minus 8, giving us 2.0 Newton per coulomb. Then in B, now from the expression, we now have that F is equal to QE, where the charge is 12 times 10 to the power minus 8 and the field intensity is given to be 2. So when we multiply, you get 24 times 10 to the power minus 8 newtons. So that's the force. Example 2. The isolated point charge of Q equal to plus 15 microcoulomb is in a vacuum. The test charge is 0.2 meter to the right and has a charge Q0 is equal to plus 0.8 microcoulomb. Now determine the electric field at P. So you see the diagram shows the force, okay, the force experienced by the charge at the point P. So now we calculate the electric field at that point as shown in the second question. Now we say E is equal to Q over 4 pi epsilon 0 r square, and that will be equal to 9 times 10 raised to the power 9 multiplied by 15 times 10 to the power minus 6 divided by 0.2 square. 15 times 10 raised to power minus 6 is because it is microcoulomb. Okay, and that gives us 3.375 times 10 to the power 6 Newton per coulomb. Now, example number 3. Example 3. Two positive point charges Q1 equal to plus 16 microcoulomb and Q2 equal to plus 4 microcoulomb are separated in a vacuum by a distance of 3 meters. Find the spot on the line between the charges where the net electric field is 0. Now, solution. If you look at the diagram, you see that the two charges Q1 and Q2 are separated by a distance of 3 meters. Now, let the points be P such that the electric field E1 experienced by Q1 and E2 experienced by Q2 will be 0. So the resultant will be 0. So that means it simply shows that at the point P, the electric field due to the two charges will be equal to ensure that the resultant or the net electric field will be 0. So that means that E1 will be equal to E2. So which gives us that 16 times 10 raised to power minus 6 over 4 pi epsilon 0 d square is equal to 4 times 10 to the power minus 6 over 4 pi epsilon 0 into 3 minus d all square. So when we cancel out, we now have 4 into 3.0 meter minus d is equal to d square. Then therefore we have a quadratic equation in which we are going to solve. We have two solutions. That will be 2 into 3 minus d is equal to d, and 2 into 3 minus d is equal to d. So because this equation is equal to minus d, so we have that d, solving the equation, we have that d is equal to plus 2.0 meter and plus 6.0 meter. So far we know that the distance between the two charges is 3 meter. Therefore, the distance of 6.0 meter can never be between them. So we neglect it. So we now ignore that. Then we now have that the distance between the d is going to be plus 2 meter. Okay. Then we move over to electric potential. We say that in an electric field where force of attraction or repulsion acts between charges, that work must be done against the field in order to move the charges against the field. So this is just like in a gravitational field, whereby force must be done against the gravity to move a point, to move a mass from one point to another in the gravitational field. So we now say that if the work is done against the field, the potential is 0, is positive, sorry. But if work is done by the field, the potential is negative. So we now say that the point of positive potential are said to be at higher potential than the point of negative potential. So therefore, positive charges move from a point of higher potential to a point of lower potential, while negative charges move from a point of lower potential to a point of higher potential. So therefore, we now define electric potential as the work done in bringing unit positive charge from infinity to that point against the force of the field. So we can also define it as the work done per unit charge by the force of electric field in moving the positive charge from that point to the point of zero potential. So now we have expression for electric potential. So the expression is given by the electric potential V is equal to W over Q. That is work per unit charge as we defined earlier. So the unit of electric potential is in joule per coulomb. Therefore the work done is given by W is equal to QV. Then electric field intensity and electric potential are related as follows. We have the electric field intensity E is equal to electric potential over D, where D is the distance between the 2 points in the electric field. So therefore we now have that V is equal to ED, which is also the same thing as ER, where D or R is the distance between the 2 points. So we now recall that E is equal to Q over 4 pi epsilon 0 square. That means V is equal to Q over 4 pi epsilon 0 R square multiplied by R. So finally giving us that V is equal to Q over 4 pi epsilon 0 R. So that's for the electric potential. Now you have your assignment. Question A. An isolated electrically charged sphere of radius R and charge Q is supported on an insulator in A of permittivity epsilon 0. Write down, question I, an expression for electric field intensity on the surface of the sphere. II, an expression for the electric potential on the surface of the sphere. III, a relationship between the electric field intensity and the electric potential at the surface of the sphere. Then question B. Question B. The plate of a parallel plate capacitor 5.0 times 10 to the power minus 5 meters apart are maintained at a potential difference of 5.0 times 10 to the power 4 volts. Calculate the magnitude of I, electric field intensity between the plates. II, force of the electron. III, acceleration of the electron. So you submit the assignment in the Google Classroom. So thank you very much for listening.